Okay, so up to now we have discussed that why we require the emitter resistance in the fixed bias circuit to improve the DC stability of the circuit. So RE resistance is actually very much required in the case of the transistor circuit to improve the DC stability. Okay, so RE resistance is actually required to improve DC stability in the circuit. Okay, so this is the importance of using the RE. Now we will see the actually transistor in the transistorized circuit. What happens? It is also providing, that means there is a DC signal, and in spite of that there is a AC signal. This DC signal that will be provided like this. Okay, now this DC signal, this is your AC signal and this is your DC signal. Now this DC signal is provided to stable the Q point, and this AC signal is provided in the transistor, which will be amplified at the output. Okay, this will be reflected at the output. We don't want DC at the output. Now, so in the transistor you will understand that the transistor, the DC signal is applied for the stability purpose, AC signal is used for the amplification purpose. Now we have seen in previously the DC analysis, and we have seen the importance of being connection of RE in the output terminal. Now whenever we have drawn the AC equivalent circuit, okay, now I am just drawing the AC equivalent circuit of the transistor whenever we have connected the DC as well as AC. Now to draw the AC equivalent circuit, all of you know that to draw the AC equivalent circuit we must short circuit the voltage source present in the circuit. So this is your transistor. 1 minute. So this is your transistor, and there is a, suppose there is a resistance present, base resistance. Okay, so this is your Vs, AC voltage present, this is your RS, and this base there is a resistance also, base resistance RB. This will be connected to ground because these are short circuited. You can look into the diagram. This will be your short circuited. So if we don't want to connect this resistance, that will be also be not required. So this will be your base resistance, and this will be your emitter resistance. And in the collector terminal, the collector this will be your collector resistance, this will be your emitter resistance. Okay, so this is your source resistance, this is equivalent to your AC signal. Okay, so that is the case. And also this voltage is the input voltage, so input is applied here. This is the actual input being applied here. Okay, you can see that the AC signal is being applied here, Vs, and this is your voltage at the transistor, at the input of the transistor. The actual AC that have been fallen is Vi. Okay, so this is the difference. This is the actual AC voltage being applied here, and this is the actual input voltage being fall onto the transistor, that will be amplified, that will be amplified. Okay, now what happens if you just make a loop KVL here, then you can see Vs is equal to, just ignore in this case, I am just ignoring this resistance. Okay, okay, so now you will be very much comfortable. Okay, now this voltage and this voltage, so this KVL like this. So Vs minus Vi, okay, minus Vf. Vf is nothing but IE into RE. So that is your voltage drop across this RE. We have considered this as VF, feedback voltage, because this feedback voltage is a negative feedback voltage. Whatever we have discussed here, this RE, this voltage IE into RE. Okay, this IE into RE is nothing but your negative feedback voltage. Okay, this is your negative feedback voltage. This feedback voltage actually reducing the input and also increasing the stability, so that will be nothing but a negative feedback condition. Okay, so that's why we have considered here the voltage as VF, feedback voltage. So this input voltage, actual input voltage falling onto the transistor, is nothing but Vs minus Vf. Vi equal to Vi minus Vf. So Vs is the source voltage and this is your source voltage, and Vf is your feedback voltage. Okay, Vf is your feedback voltage and Vi is the actual input falling onto the transistor that would be amplified. Actual input fall on transistor input. Okay, that would be amplified. So what happens, this Vf will be a presence of the emitter resistance. If we don't give any emitter resistance, if we short circuit this, don't use any emitter resistance, then this Vf will be 0. So whatever supply we are applying here, that will be totally fall onto here. But what happens due to the presence of this feedback voltage, the actual input, this Vs will be, this will be negative feedback, so it will try to reduce the effect of the input. So Vs minus Vf, so Vi equal to Vs minus Vf. So due to the presence of this emitter resistance, this Vf will increase or Vf will present, so that's why this Vi will be decreasing. So if Vi will be decreasing, then what happens, output voltage will be decreasing. So what happens, that our main aim out of the transistor is to amplify the signal, Now if Vi is reducing, then V0 will be reducing, so the amplification is actually disturbed. Due to the presence of this RE, or due to the presence of the voltage developed across the RE, that is the feedback voltage. So we require RE due to the improvement of DC stability. But at the same time, we don't require RE because it is reducing the Vi, input voltage, in the AC analysis. So it is actually improving the DC stability or improving the Q point, but at the same time during the AC analysis is reducing the input voltage. So we require RE, but at the same time we don't require RE. So that is the paradox is being created. So we have to solve with that. How we can solve with that? We have to apply a bypass capacitor across this emitter resistance. So if we just apply this bypass capacitor, then what happens, the problem will be solved in a second. So this will be your emitter resistance and we have to apply a capacitor across this. So that's all, nothing else. Okay, now what happens, all of you know that this capacitor is open circuit at the DC voltage. Capacitor is open circuit at the DC voltage. So what happens at the whenever we don't apply the DC voltage here or the DC analysis, during the DC analysis this capacitor will not be present. This will be just like a open circuit. Okay, so the original stability analysis, all of the things will be present there as it is, but during the AC analysis capacitor is short circuit during AC analysis. So what happens in the AC analysis, the capacitor will be short circuited, so there will be no effect of RE because all of the current that will be flowing like this. So there will be no effect of this RE, or no voltage will be developed across this RE. So as the no voltage will develop across the RE, so this condition, that means your Vi will be Vs minus Vf. So this Vf will be 0, this Vf will be 0, so Vi will be approximately equal to Vs. So the AC analysis there will be also no problem. So just by applying a capacitor across the emitter resistance, same time we are improving the DC stability as well as we are improving the AC analysis condition. That means your input voltage will not be reduced by the amount of voltage feedback voltage. That means Vs equal to Vi minus Vf. This condition is also eliminated. This VAP is also eliminated at the AC analysis, but this VAP is also present during the DC analysis. So that the use of that is called the bypass capacitor. Bypass capacitor that will be used to bypass the emitter resistance. Bypass capacitor at the emitter terminal. Bypass capacitor present at the emitter terminal of the transistor. Okay, so that will solve all the problem. Okay, hope you understand this.